Good morning, ladies and gentlemen. More and more derivatives. So far you do know that the derivative of sine is cosine, and the derivative of cosine is negative sine, along with your power rule, all those lovely properties of derivatives, the sum of a function is the sum of its derivatives, basically, blah, blah, blah. And we're going to look at a couple more here, and we're going to look at the tangent function first. Well, tangent, because we don't know what it is, okay, so what we have to do is we don't know the derivative of tangent, but we do know that we can take the derivative of the tangent as the sine x over the cosine x, okay, because we do know the derivative of sine and cosine. So that's the quotient rule, which is going to be the derivative of the top. Derivative of sine is cosine, times the bottom, which is cosine, minus the derivative of the bottom, which is a negative sine x, times the top, which is a sine x, all over the bottom squared. Okay, so what we really get here is we get a cosine squared x. Sine x times sine x is sine squared x. That's a negative, and a negative, that's a plus sine squared x. All over a cosine squared x. Oh, what is that up here? That is one of your trig identities. It happens to be called the hammer here at West. So we really look at this as 1 over a cosine squared x, which actually, reciprocal identity, is going to be secant squared x. That is my derivative of tangent. So the preferred derivative of a tangent is called a secant squared x. Okay? And we're going to move on to our next one, cotangent. Well, I don't know what the derivative of cotangent is, but I do know with my trig identities, cotangent is cosine x over sine x. And I do know that I can use a quotient rule here. The derivative of the top, cosine is negative sine x, times the bottom, sine x, minus the derivative of sine is cosine x, times the top, which is a cosine x, all over the bottom squared, which is a sine squared x. Well, multiply this out, well, that gives me a negative sine squared x minus a cosine squared x over a sine squared x. Okay? Oh, look at that. There's a modification of the hammer. Remember, sine squared x plus cosine squared x equals 1. So a negative sine squared x minus cosine squared x equals negative 1. Okay, so I can use that, and I can say this equals a negative 1 over a sine squared x. Why, look at that. 1 over sine, well, that's a cosecant, or I'm sorry, 1 over sine. Am I in the right spot? I am. It is a cosecant. It's a negative cosecant squared x. Is my preferred form of cotangent, negative cosecant squared x. And I say the preferred form because wouldn't you rather look at a cosine or a cotangent and say the derivative is negative cosecant squared than go through all of this identity business, okay? So we're going to take a little gander down here, excuse me, at the secant. Well, I don't know what the derivative of secant is, but I do know that the secant has a trigonometric identity that is called a 1 over a cosine x. And then I can see, ooh, a quotient rule. The derivative of the top is 0 times the bottom, okay, minus the derivative of cosine. That's a negative sine times the top, all over the bottom, cosine squared. Okay, so what that gives me, well, I know that's gone, a negative and a negative, that gives me sine x over cosine squared x, okay? That is not my preferred form of my secant, okay? What we're going to do is, because I have one term in the denominator, is we're going to look at this as a sine x over a cosine x times a 1 over cosine x, okay? I know sine times 1 is 1, cosine times cosine is cosine squared, which actually gives me what? Sine over cosine. What is a sine over a cosine? That's a tangent x, and 1 over cosine, well, that's a secant x. Now, that is the derivative. However, my preferred form of that is called a secant x tangent x. And yes, you do have to have the argument portion written in both of them, because if it didn't have an argument in it, I don't know what the secant is. So the derivative of secant is secant tangent. Okay? Whew! There's a third one that we now, oh boy, now we go into the cosecant. Well, again, I don't know what the cosecant is, but I do know the cosecant has an identity of 1 over sine x, which means I can take a quotient rule. The derivative of the top is 0 times the bottom, which is sine, minus the derivative of sine is cosine times the top, all over the bottom squared. Look there, it's a sine squared x. Well, what happens here is that's gone. I get negative cosine x over a sine squared x. Here we're going to do the same thing because that's kind of ugly. Let's look at it with all those trig identities you guys did in pre-calc last year. Look at it as a negative cosine over a sine. I'm going to split this little bugger up, times 1 over a sine x. What does that equal? Well, negative cosine over sine, that's negative cotangent x. And then that's times 1 over sine, that's a times a cosecant x. And my preferred form of that is typically reverse of that, but think of the derivative of cosecant is cosecant x cotangent x, and I forgot a big portion of it. So I'm going to take that guy and I'm going to slide him over, because what did I forget? I forgot that whole negative symbol. It's negative cosecant x cotangent x. Okay? So I just slammed out at you 1, 2, 3, 4 more derivatives that you have to commit to memory. Just looking at, whenever you're taking the derivative of cosecant, trust me when I say, you just need to know it as negative cosecant x cotangent x, because you do not want to have to go through all of that business to get that. So it's one of those things you just got to memorize. Okay? Now, this next slide, derivatives that you already know. Okay? The ones you already know. And there are still more to come. A lot more to come, more than double what you're looking at. So remember, you know the power rule, x to the n. That's n, drop the power, times x to the n minus 1. Now you got the derivative of sine is cosine. Derivative of tangent is secant squared. Derivative of secant is secant tangent. Now notice how what I did here is I put all my cos on the right, and what do you notice about all the the derivatives of the co-functions? They're all negative. So derivative cosine is going to be a negative derivative. Derivative cotangent is a negative. Cosecant is a negative. All the cos have a negative, okay? So what we need to do is take these 6 new derivatives, along with the ones that we know, or these new 4, you already knew, sine and cosine, okay? And take these 4 and apply them into some new problems, okay? So what we're going to do is we're going to do a few problems here. We're going to do 1, 2, 3, 4, 5 problems, and then we're going to do some simple harmonic motion, okay? So One thing to know, if you ever look at this and you want to say y prime equals, okay, x times tangent x is 1 times secant squared x, okay, please understand that is wrong. You will never take the derivative of one function times the derivative of another function. You have to identify that there is, like I said, a product in here. And when I am multiplying a function of x times a function of x, I have to use the product rule, which means if I'm thinking this is u and this is v, remember u times v, if I'm taking the derivative in terms of x, I think of it as the derivative of the first one times the second one plus the derivative of the second one times the first one, okay? So what I'm going to do is I'm going to say y prime equals, well, the derivative of u is 1 times the tangent x plus the derivative of the second one, tangent, is secant squared x times x. And what I'm going to do is I'm just going to rearrange that, say y prime equals tangent x plus x secant squared x. And there's really nothing I can do identity-wise to simplify this derivative. So I circle it and I am donezo, okay? This next problem, here again, I have another product. Whoa, got a little carried away there. What I would encourage you to do is hit pause and see if you can get it right, okay? What? My y prime is the derivative of my first term, which is 2x, times my second term. So first, derivative of first times second, plus derivative of second, negative cosecant x, cotangent x, times the first term, parenthesis on there. Now what I'm going to do is I'm going to look, oh, this is just 2x cosecant x minus x squared cosecant x cotangent x, okay? Technically, y prime is there. You could leave it like this, but what I'm going to encourage you to do, because sooner or later, the reason we're taking these derivatives is so that we can set them equal to 0 and find flats on the curve, okay? And the only way we're going to do that is through factoring. So I would prefer, personally for me, I can see there's an x and a cosecant I can take out of each one. So I would look at it as x cosecant x times 2 minus x cotangent x, okay? And it's really important that you could see either one of these two answers, because it's very possible that these could be a multiple choice question on the AP test, and you never know which one you're going to run into. You always have to see equivalence of what you started with, okay? Why don't you go forward here, and why don't you see if you can try number 3. My mouse is not working here. Now, if I were a betting man here, which I am, most people, I'm assuming, are going to say, hey, got a function of x times a function of x. Means I need to look at that first one as u and the second one v. So I'm like, okay, y prime equals derivative of cosine is negative sine x. Derivative of the first times the second, which is a tangent x, plus the derivative of tangent is secant squared x times cosine x. Okay, and then you're getting in here and you're like, oh, wow, that's getting pretty ugly. Thinking back to pre-calc, all those trig identities to simplify. Well, it's really a negative sine x over 1 times a sine x over a cosine x plus, secant. Well, didn't we try to look at everything in terms of sines and cosines typically? Times cosine x, and that one's over 1. Okay, and then you're looking at this thing and you're like, whoa, check it out. That cosine reduces and gets rid of that. So I'm really looking at negative sine squared x over cosine x plus 1 over cosine x. Hey, isn't that sweet? I got common denominators already, which is negative. Oh, actually, I'm not even going to put it that way. I'm going to flip-flop it. I'm going to say, oh, that's 1 minus sine squared x over a cosine x. And then, modification of the hammer. Remember, if you had your sine squared x plus your cosine squared x equals 1, well, if I subtracted a sine squared, I could say cosine squared x equals 1 minus sine squared x. That's why I rearranged that. So I'm like, well, that's kind of nice. This is a cosine squared x over another cosine x. Holy smokes, look at that. Because now I know I can reduce that with that. So that's just going to equal a cosine x, okay? If you did that and you got that, you did a phenomenal job, okay? And you went all the way through this problem, a very difficult pathway, okay? And we really wouldn't want to, personally for me, I wouldn't want to do one this way because I'm thinking back to pre-calc into my trig. Trig is my most favorite subject to do. I absolutely love identities. And if I look at this, I have the cosine x times a tangent x. And because I'm multiplying these two trig functions, sometimes I can simplify that trig function mess really nice and sweet, and I can redefine my trig function and say, oh, that's really y equals sine x. Now I'm going to take the derivative of my simplified version of my function, okay? Notice, if I simplify it first, how much easier the derivative was. Now, does that always happen? No, it does not always happen. Well, how do I know when I need to do that? The only way you know that you're going to try to do that is through practice, 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 and working problem, okay? And by learning from mistakes. Now, when I look at number 4 here, because that's a sum in the denominator, I can't really reduce this thing in any way, shape, or form, or make it any nicer, okay? And I'm just going to take the derivative of this quotient. So I'm going to say y prime is going to equal the derivative of the top. Well, the derivative of cotangent is negative cosecant squared x times the bottom, 1 plus cotangent x, minus, okay, so there's my first one, and there's the second one, minus the derivative of the second, or the bottom, oh, that's another negative cosecant squared x, times the top, which is a cotangent x, okay? Now, I've taken the derivative. My calculus is done. I need to simplify my derivative now. Oh, my derivative's not done yet, Kruger. We did a quotient rule. We still need to put that over the denominator squared. And that's a 1 plus cotangent times a 1 plus cotangent. I would never really want to expand that denominator out because in the end, when I reduce by factors, and I'm already factored there. So what do I need to do? Well, if you look the long path here, y prime is going to equal, well, I'm going to have to distribute here. I get a negative cosecant squared x minus a cosecant squared x times a cotangent x. And I can see this is cosecant squared times cotangent squared. A double negative makes that a plus cosecant squared x cotangent x all over 1 plus cotangent x quantity squared. And when I'm looking here, hopefully you're identifying that guy and that guy. They're like terms. This is just like an x squared y plus an x squared y. So they're like terms. They cancel each other out. And I can get to y equals negative cosecant squared x over 1 plus cotangent x quantity squared. Okay? And what I would do is I would look to see if I can simplify that. Well, it would bring me to what I would think about Pythagorean-wise. Okay, I know the sine squared plus the cosine squared. I better put my x's in there. I know that equals 1. Okay, so if I need a cosecant, how am I going to get a cosecant? I'm going to divide everything. If I divide everything by a sine squared, I can get this to where I have a cosecant squared x. What does that equal? 1 plus cotangent squared x. Okay? Now this is 1 plus cotangent squared. It's not 1 plus cotangent squared. This guy has a middle term in it, so it's not going to go away. So even if I tried to replace this in my numerator, it is not going to reduce because it's not 1 plus cotangent quantity squared. So really what I'm looking at is I have nothing here to reduce, but you have to look at your trig identities, and I guarantee you, okay, this would be an acceptable answer for me right here. If you type that into your calculator, it's not going to be anything near that. Okay, it's going to be about 6 different steps deeper into 1 over, I think it's sine x plus cosine x quantity squared or something goofy like that. We can get there with trig identities, but I don't need to, because if I had to find when this function was undefined or 0, I can do it already. I have a solvable equation where I'm at right now. Okay, so why don't you come here? Why don't you try to do number 5 quick, and I will be back in a flash. Maybe. Okay, if you are looking at this one and you are thinking product rule, what I'd like you to do is I would really like you to look and say, there's a sine. What is a sine x times a cotangent x? Cotangent is cosine over sine. You got to keep these trig identities in the back of your mind. You got to remember, this one just might simplify. If I distribute that sine, I have the sine times the cotangent here as a cosine over a sine. Look at that. My sines cancel out. So really, I can simplify this function to y equals sine x plus cosine x. I do not have, there is no product here, which is a very happy thing, because now I can just use one of those properties. The derivative of sine is cosine, and the derivative of cosine is negative sine, to say my derivative should be cosine x minus sine x, and I have the derivative of that little bugger. Okay. Next thing we're going to do is we're going to look at simple harmonic motion here in a second. Okay, simple harmonic motion, the motion of a weight bobbing up and down at the end of a spring, not dampened. What in the heck does not dampened mean? Well, what not dampened means is we are going to assume this object is going to continue in perpetual motion, meaning once we set it in motion, gravity is going to have zero effect on it, and it's just going to move forever and ever and ever. Now, logically, we know that is not going to happen, but we are not doing a dampened factor on that, which means the spring is going to bounce as high as it is as high and low as it does the first cycle as it does all cycles, okay? Now, a body is moving in simple harmonic motion with a position function, f of t, equals 2 minus 2 sine t in meters, and t is in seconds, okay? So this position function here, this is a position function, and it is, in terms of time, giving me, plug time in, I get meters away from the ceiling. Now, why is the position from the ceiling important? Because our point of reference is the position of the ceiling. Every way, personally, for me, I need to think about this is back-asswards of logic, okay? Because when I'm thinking of this, if my spring is moving down, okay, so here I'm going to come down here, and I'm going to say, here's my ceiling. So I have this thing coming down, and it's on a spring, and then it's going to come down, and I have this little weight on the spring. Now the position is measured from the ceiling, okay? So I need to think about something. As my spring is moving down, what is happening to the position of the object in relation to the ceiling, okay? What is happening? As it goes down, this object gets further from the ceiling, right? So I need to think here, I need to come back here and think, okay, moving down, f of t is increasing. And it's increasing because it's getting further away from its point of reference. Which, remember, what does that mean? Well, if f of t is increasing, what does that mean for v of t? Well, if a function's going up, that means v of t is some positive number, right? Okay. Now, I'm going to come back down here. Well, what happens when my spring is moving upward? Well, the distance between the ceiling and the object is getting smaller. So moving up, we know f of t is decreasing. And it's decreasing because the distance it is from the ceiling is getting smaller and smaller as the object is moving upward, which means if it's decreasing, that would imply my velocity is negative, right? Okay, so I just need to keep that in mind, okay? And what these are going to do, what this simple harmonic motion problems do, they are kind of like a specific application of displacement, velocity, and acceleration, which are in trig functions. They're specific applications, and they show kind of how these three functions relate with each other, meaning displacement, velocity, and acceleration. So what we're going to do is not forget about this, okay? When it's moving up, my function's decreasing, and when it's moving down, my function is increasing, and here is my function. So what we're going to do is we're going to come down there. Well, okay, so if that's my position function, f of t, okay, we're going to quickly find the velocity, speed, and acceleration at time t. Well, if this is f of t, v of t is the derivative of f of t, right? So this is going to be f prime of t. That's what v of t is. Well, I know the derivative of 2 is 0, and that's going to be the derivative of sine is cosine, so this should be negative 2 cosine t, right? And because this is my s of t, okay, that's going to be my speed. Speed is the absolute value of velocity. And I could really simplify that a little bit if I wanted, and I could pull that constant and say it's 2 times the absolute value of cosine t. And I can really kind of drop that negative off because it's inside the absolute value. It really makes no difference to me because when it comes out, it's going to be there. This is just my simplified speed function, okay? In my acceleration function, I'm going to make that one an orange. My acceleration function is going to be v prime of t. So when I come back here, well, the derivative of cosine is negative sine. So that's going to give me a negative negative 2. That's 2 sine t, right? And what we are going to do, I'm going to keep all these different. So let me just get in here a second. And that way, because we're going to graph them all. And let me make my S of t is going to be my speed. And we're going to say that's absolute value negative 2 cosine t, like I said before, which if we simplified it, cosine, and I do need the absolute values on that cosine because remember the cosine oscillates between positive and negative. We have to make sure it's always going to be positive because it's speed. So what we're going to do is we are going to come down here and we are going to graph 2 cycles of this bad boy. So I'm going to say this is like 2 pi and this is going to be like 4 pi. And the first thing we're going to do is we're going to graph position. So position is graphing that 2 minus 2 sine t. Well, remember, okay, this shifted my sine function up. This gave my sine an amplitude of 2. This made me start down rather than start up, and all that good stuff to go. And because I'm going to graph 2 cycles, I'm going to find my middle of this guy, and I'm going to call that 3 pi. And I'm going to find about the middle of this guy, and I'm going to call that pi. So here's my pi over 2. Here's my 3 pi over 2. Here and here. Okay? So remember, if I'm graphing, okay, if this whole function is shifted up, I need a line. And I'm going to call that line right here. And I'm going to make that line crumb. I'm going to make it, what color do I make that one? I can't make it blue. What color do I make it? I'm going to make black. I'm going to make it black. Okay, so my position is going to be black. So I know I'm kind of starting here. Okay, and that's like my midpoint. That's like my midline when you guys graph your trig functions with midline. I'm going to get him where he needs to go. Okay, and then I'm going to take black, and remember, because it's a sine, okay, your sine, when you're looking at your unit circle all the way around, okay, we want 1, 0. There's my sine. So my sine started at 0, then it went to a 1, and so forth. So I could see negative 1, 0. In my intervals of pi, okay, I was at 0, then I was at 0, then every interval of pi I was at 0, and I'm at 0, and I'm at 0. Okay? Now, my amplitude was 2. Okay? But because this is a negative 2, rather I'm not gonna start and go up to 4. I gotta start, and because it's reciprocated, I gotta go down, and then I'll go up, and then I come back to my 0, then I come back down, and then I come back up, then I come back up to the top. I can't do this here very well. And I'm going to try to make this sine as best I can. Oop, that was really bad there at the end. So I got pretty dang close. And remember, that's my position function. I'm going to get rid of my little ceiling diagram here in a second. And hopefully I don't need my unit circle. That's just stuff you guys are supposed to know and remember and love. So that is my f of t, which is position or displacement. Okay? So from there, what I'm going to do is get rid of this little bugger. Okay. What I'm going to look at here is notice what happened, the spring is moving in simple harmonic motion with its position function. So it's starting 2 meters off the ceiling right here. Then what's happening is if it's going down, okay, like so, what's happening? Okay, so if it's decreasing, is it moving up or down? It's moving up because that displacement is getting closer to 0. So I'm going up here, right? And then I go down. So I'm going up because now I'm going down. Then I go up. And then I go down. And I go up again. Okay? So the weird wonky thing is when I'm looking at this position graph, when my position graph was going down, my spring's actually going up, but that's only because the point of reference is on the ceiling. Okay? So we're looking at that. We are also going to now graph our velocity and our acceleration. So if I come here for my velocity, v of t, well, that's just a -2 cosine t. Well, that one's not shifted up or down. Now, where was my cosine? Well, I don't have to worry about that because I can actually look at my position function and say, ooh, it's going to be flat here. It's going to be flat here. So those are my zeros of velocity, and I can trace that graph right off of there. Okay. Now, also, my velocity, well, I started out going down, didn't I? So if I started out going down, where is my acceleration at 0? Well, I can put a 0 in here, and I'm at -2, not acceleration velocity. So it goes down here, and I'm going to come up, come down, up into my 2, wink, 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 and somewhere down here should be about where I am. Okay, so I can see my velocity curve. Kind of like that. So, made that one a little too long. So this is v of t, or velocity. Okay. Now the last one I'm going to do is my acceleration curve. My acceleration's orange. Well, if I'm flat here on my velocity, and I'm flat here on my velocity, and flat here on my velocity, flat here on my velocity, okay, I could be using my trig functions, or I could be using my flats here as well. Well, what's happening with the velocity? Well, if this is increasing, that means I'm coming up, right? Sine, and then I come back down. Then I go to 0, and I come back up, back down. I get them there, and then here's my acceleration curve, and it's kind of jumped up a little bit. That was bad, I missed it. So there is a of t, or my acceleration curve. Okay, so as I'm looking at all these, I'm just seeing what is going on. We're going to relate all these graphs: position, acceleration, velocity. Okay, and if I had to graph my speed, well, heck, if I had to graph my speed, all I really need to do is come down here. Well, yeah, I'll graph my speed in red, and I'm going to say there's my pi, my 2 pi, and my 3 pi, my 4 pi, and I got halvesies, 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 halvesies. All I need to know is I'm graphing that blue one, right? So I can see I'm 0, 0, and I come up to 2. And then I go down, but I'm back to a 0 here. And then I come up to a 2. And I come back to my 0 here. And then it looks like this guy goes down. Well, absolute value, well, what's negative is positive. So I go, wink, Point. And there's my speed curve. Okay, so why did we graph all these? Well, we graphed all these because we're going to use them. Okay, and again, please remember up here, moving down, f of t is increasing. Okay, because my spring is hung off the ceiling. So when the spring is moving away from the ceiling, I'm gaining distance, meaning distance away from my point of reference. Therefore, function is increasing. And when the distance is getting smaller, it's decreasing. Okay, and that's when it's moving towards the ceiling. Okay, so we have all these wonderful graphs that we can look at. Okay, I mean all kinds of stuff we can look at here, and we can look at the position function, and we can say, oh, okay, well, yeah, I guess it makes sense if this is the ceiling here. Okay, because that's my point of reference is the ceiling is my 0. That's my ceiling. And if I'm starting at 2 feet and then I go down to 0, oh, what it must be starting what? It must be going up to the ceiling and then down 4 feet off or 4 meters away from the ceiling and then back up to the ceiling. And then back down, okay, don't get all tied up. And then it's going back up, and it's kind of right there. It's where it started from now. Again, it's halfway through, okay? So what are we going to do here? We're going to use these curves in a minute. What we're going to do is we're going to find position, velocity, speed, and acceleration at pi over 6, okay? Well, what is f of pi over 6? Well, f of pi over 6 is going to be 2 minus 2 sine pi over 6, okay? And bottom line, let me come back. What we're doing is we're saying, hey, we can answer lots of questions off of this graph, okay? Meaning, when I'm here looking, is the object speeding up or slowing down at pi over 6? Well, I can come back here really easy and I can look at this, okay? And I could say, well, okay, well, here's pi over 2, kind of going off chart again. So pi over 6 is back here, right? Pi over 6 is somewhere back in there. I don't really care where it is in there. But I can look, and what was the question I asked? Is it speeding up or slowing down? Well, hey, I can get that off my position curve really easy. Because I can look at my position curve, and remember, speeding up, slowing down, we said, hey, what's it doing from here to here? Well, my curve is getting less steep. So if my curve is getting less steep, what's the object doing? Oh, it's slowing down, okay? And I could look at the next one, and I could also say, is the object moving up or down at this time? Oh, well, it's pretty simple to see. I mean, I can look at my position curve and say, oh, it's approaching 0. It's going down. It's actually going up, excuse me, because my position is getting less. It's approaching 0. So, I mean, I could look at that. But the whole point of this next page is what if we don't have a graph? What if we don't have a graph? Now, all we have are the position, velocity, speed, and acceleration functions. Well, what we're going to do is we're going to look at this. And don't forget, pi over 6, okay? I got 1, 2, 3. Pi over 6 is this first pi guy right here, which I think my sine is a half, and it's root 3 over 2. Okay, so you guys, like there's your pi over 6. So I'm assuming most of you are unit circle dependent, but you got to get off of that. It's 2 minus 2. Well, what is the sine of pi over 6? Oh, it's a half times a half. Well, that's 2 minus 1. Oh, the position at pi over 6 is 1 meter from the ceiling. Okay, well, what's my velocity? Well, v of pi over 6. Well, I can plug that in because I know my velocity function is -2 cosine t, but rather than a t, I'm putting in a pi over 6. So I can look at this and I can say, oh, negative 2 cosine of pi over 6, well, that's my times root 3 over 2, which the 2's cancel, and I get negative square root 3. Now remember, this is velocity, so that's meters per second. Okay, I can look at my acceleration. I can look at a at pi over 6. Well, my acceleration function, or actually, before I do that, I might as well do my speed first because that makes sense. So speed, my s of pi over 6, well, hey, that's really easy because that's just taking the absolute value of that. So it's square root of 3 meters per second. That's all. The speed's just velocity, but positive. So what's my acceleration? A of pi over 6. Well, that's coming out to 2 sine t, where t is pi over 6. Okay? And then that's 2, because the sine of pi over 6 is a half, which gives me 1. And remember, it's acceleration, so that would be meters per second squared. Okay? So I can take all these functions, and I can take position, velocity, and acceleration. Those are the main ones I'm doing. And speed is easy because we're always doing position, velocity, and acceleration. Speed is just absolute value of velocity, so that's kind of a no-brainer. If it's negative, pull the sign, that's your speed. But is the object speeding up or slowing down? If we didn't have a graph, how do we know? Well, here's how I know. I know this object is slowing down. Okay? This object is slowing down. And the reason I know it's slowing down is because in my analysis between velocity and acceleration, I know v of pi, I better write this right, I know v of pi over 6 is what? What was v of? Was negative, and a, got my d, and I forgot, and a of pi over 6 equaled positive. So what did that mean? Well, that meant velocity and acceleration were opposite signs, because v of t and a, I better use a little a of t, are opposite signs. And that is a calculus justification of why the object is slowing down. Velocity and acceleration are working opposite each other, therefore slowing it down. Well, is the object speeding up or slowing down at this time? Well, I don't know. What is it doing? Is it moving up or down? Sorry, not speeding up. We already did that. Is the object moving up or down at this time? Well, I would say pretty simply, it's moving up. And the reason it's moving up, okay, what do I see about v of pi over 6? Well, v, the velocity at pi over 6 is negative. And if the velocity is negative, what does that mean is happening to my position function? Moving up, because v of pi over 6 is negative, therefore position is decreasing, okay? Because my derivative's negative only when its original function was decreasing, because the position is decreasing. And if the position is decreasing, means it's moving toward ceiling, which is up. Okay? Ceiling is the point of reference. The object is moving towards the ceiling, okay? And that's what I'm looking at there. This next page here, quick, is looking at describe the motion of the body. Well, let's say I didn't have the function, and all I had was a graph. And I knew this blue graph was my position function. Well, I can see, describing the position, okay, I can see t equals 0. It starts at 2 meters from ceiling. Okay, because here's the ceiling. Here's 2 meters away. And then what happens? Then goes up 2 meters to ceiling, right? And that's at pi over 2. Then down to 4 meters at t equals 3 pi over 2. Then it oscillates between 4 meters and 0 meters every pi seconds. That's describing the motion. I can see my position. I'm starting here. It goes down or up. Okay, so it goes up to the ceiling, down 4 meters, back up to the top of the ceiling, down 4 meters. Then it comes back to where it started. Okay, well, describe the speed. Well, here's my velocity, and ignoring the velocity there, look at my speed, and I can see what's going on, the position. I can see accelerate, or I can see positions positive, negative, and all that good stuff. Speed. Well, what do I see about the speed? Well, here's my speed curve right here. It's the absolute value of velocity, the first derivative. Okay. What do I see? The speed is at a max, okay, every pi seconds. Because here's the speed, maxing out, maxing out, maxing out, maxing out. There's my speed. What do you notice about that speed on your velocity curve? Well, that is your velocity curve reciprocated, but what do you notice about that speed on your position curve? Oh, it's a point of inflection. What do you notice about that speed? Maximum speed. Maximum speed. It's a point of inflection. What happened at that point of inflection? See, I can get that off my position curve too, because that is where it is the steepest. Okay, so I'm increasing, get more steep, less steep, less steep, less steep. More steep, more steep, more steep. Less steep, less steep, less steep. See, I can get all that. So every pi seconds, okay? F of t is at a point of inflection, and object is halfway between top and bottom every time it's at its max speed. And when at 0 and top, okay, meaning bottom, minimum, maximum of position, okay. Hold on, let me write this. So let's say my speed is at 0 at top and bottom, or when it's changing direction. Okay, I can see negative to positive on my velocity curve, change direction, down, up. Okay, I can see positive, negative, change in direction. I can see down, up, changing direction. I can see all of that good stuff on there. And when the speed's 0 here, pi over 2, and when the speed is at pi, and when the speed is at 2 pi, and when I'm at 3 pi, I can see it all in there, right? I can see that's where my object is changing direction. Acceleration is at a max. There's the acceleration is the black one. Acceleration is at a max or min when object is at the top or bottom. Okay, so my acceleration is at a maximum right here when I'm at the ceiling. My acceleration is at a minimum or a maximum again, okay, right there, it's at a minimum when I'm 4 units away from the ceiling. Maximum when I'm at the ceiling. Minimum 4 units away from the ceiling. I can just correct or show those. And also, is at 0 when object is moving the fastest. Okay? So the acceleration is 0 when the object's moving the fastest. Well, when's the object moving the fastest? Right here at its point of inflection. Okay? Right here at its point of inflection. Acceleration is 0. Well, that kind of makes sense. Think about it. When you step on the accelerator and you speed up as fast as you want to go and you're going fast, you let off the accelerator, your acceleration is 0, and now you are at your max speed and you'll be slowing down. It's kind of nifty. So if I'm looking at my object here, here's my ceiling, spring, weight, and if this is at 4 meters, this is at 0 meters, and this is at 2 meters where it started, okay? Speed here is at 0 at the ceiling when acceleration is at max. And here my A of t equals 0. And I know my speed is at max. And here my speed is 0, and acceleration is at minimum. Okay? So, sorry for the lengthy video, but that's it. If you were here, you would have got it in a day and a little bit extra.